In this video, I'm going to give you a simple introduction on how to write the electron configuration of an element. So let's talk about nitrogen. So how can we write the electron configuration for an atom of nitrogen? So that's how nitrogen looks like on a periodic table. So the higher of these two numbers is the mass number, and the smaller of the two numbers is the atomic number, which is an integer. Now what you need to know is that in the first energy level, you have the 1s sublevel. In the second energy level, you have the S and the P sublevels. In the third energy level, you have S, P, and D. Now for nitrogen, this is as far as we need to go. The S sublevel can hold 2 electrons, and the P sublevel can hold 6, and D can hold 10. Now you want to write the electron configuration until you get a total of 7. Now for an atom of nitrogen, it contains 7 protons and 7 electrons, but we're focused on the number of electrons because we're writing the electron configuration. For ions, that number could differ, but for atoms, you just need to focus on that number. So the number of electrons in this problem is 7. So here's what we need to do. First, start with 1s. So I'm going to write 1s2 because s can hold up to 2 electrons. Next, move on to the 2s sublevel. 2s can also hold 2 electrons. And then after 2s, you want to go to 2p and then 3s. Now 2p can go up to 6. It can hold 6 electrons, but we only need 3 more. Because if you add the exponents, 2 plus 2 plus 3 is 7. So once you get up to this number for atoms, you can stop. This is the electron configuration for an atom of nitrogen. Now let's try another example. Let's write the electron configuration for aluminum. You could try it if you want to. So we're dealing with an atom of aluminum, which has 13 electrons. So you want to write the configuration up to 13. Now we're going to set it up the same way. Now if you want to, you can add the 4th energy level, which contains 4s, 4p, 4d, and 4f. Now let's put these numbers again. F can hold up to 14 electrons. So we're going to start with 1s. So that's 1s2. And then after 1s, we have the 2s sublevel. So this is going to be 2s2. And then we need to move on to 2p, then 3s. So p can hold up to 6, and s can hold up to 2. So if we add the numbers 2 plus 2 plus 6 plus 2, that's 12. We only need 1 more. So after 3s, we need to move on to 3p. Now we don't need to go up to 3p6. We only need 1 more, so we're going to stop at 3p1. So if you add 2 plus 2 plus 6 plus 2 plus 1, that will give you a total of 13. So this is the ground state electron configuration of an atom of aluminum. Now what about ions? Let's say if we want to write the electron configuration of the Fe2 plus ion. How can we do so? Now on a periodic table, Fe has an atomic number of 26 and an average atomic mass of about 55.85. So an atom of iron metal has 26 electrons. So what about an ion of Fe? Because the charge is plus 2, that means that the atom lost 2 electrons. So therefore, the Fe plus 2 ion has 24 electrons. It has 2 less than this number. So we're going to write the electron configuration based on the number 24. So let's make our list again. 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f. S can hold 2, P can hold 6, D can hold 10, F can hold 14. So we're going to start with 1s. So that's going to be 1s2. And then we're going to move on to 2s. So this is going to be 2s2. And then we're going to go to 2p, then 3s. So it's going to be 2p6, and then 3s2. Now after 3s, we got to move on to 3p, then 4s. So it's 3p6, and then 4s2. By the way, before you write the electron configuration of Fe plus 2, it's better if you write the electron configuration of the parent atom, and then from that write the electron configuration of the ion. So I'm going to focus on 26, and then I'm going to adjust it to 24. So right now we have a total of 2 plus 2 plus 6 is 10. 2 plus 6 plus 2 is another 10. So we need 6 more electrons to get to 26. So after 4s comes the 3d sublevel. Now d can hold up to 10, but we only need 6 more. So this is the electron configuration of Fe, but not Fe plus 2, because we have a total of 26 electrons. Now from this expression, you want to write the electron configuration of Fe2+. So you need to remove 2 electrons. The question is, which 2 electrons do you remove? Now what you need to do is remove electrons from the highest energy level. So that's from the 4th energy level. So you're going to take off these 2 electrons. So we could therefore write the configuration for Fe2+ as 1s2, 2s2, 2p6, 3s2, 3p6, 4s0, or you could just omit it, and then 3d6. Now, if you were to write the configuration based on this number, and if you didn't do this step first, you might be inclined to write 4s2, 3d4, and it won't be correct. So when you're dealing with transition metal ions, it's best to write the configuration of the parent atom first, and then if you have a positive charge, simply take off electrons that's equal to the charge, starting from the highest energy level. Now let's move on to our next example. So we're going to deal with chlorine. So here's the information that you need to know for chlorine. Now what I want you to do is write the electron configuration for the chloride ion. Go ahead and try that problem. Now for chlorine, we really don't need the 4th energy level. So let's start with this. We need to get up to 17, and then we're going to add 1. Chloride has a total of 18 electrons. Now for this one, we can just go straight to 18. We don't have to start from 17 and add 1. You could do that if you want to, but you don't have to, because chlorine is not a transition metal. So I just want to rephrase this one more time. For transition metals, it's best to write the electron configuration first, and then subtract the appropriate number of electrons based on a charge. For elements that are not transition metals, and if you're dealing with ions, you can go straight to this number. You could find the total number of electrons in the ion, and then write the configuration based on that. You don't have to write the configuration of the atom and then adjust it for the ions. It just simply work out that way. But you could do it both ways for these elements. So if you decide to write the electron configuration for the parent atom and then adjust it for the ions, then that's fine. For negatively charged ions, you need to add electrons. For positively charged ions, you need to subtract the electrons. So let's start. We need to get up to 18. So we're going to start with 1s. So this is going to be 1s2. And then it's going to be 2s2. After 2s comes 2p, then 3s. So it's 2p6, and then 3s2. So far we have a total of 12, so we need 6 more. And 3p can hold up to 6, so we're going to stop at 3p6. This is the electron configuration for the chloride ion. For chlorine, it's everything up to 3p5, but for chloride, it's 3p6. You got to add 1 to it.